wonderful workshop. This is joint work with some wonderful co-authors. There are 2 papers I'm going to mention here. Most of it will be about the second follow-up work with Greg. But there was an initial work with Jane, Ali, and Leon that released the stage and asked the question that we're answering here. This is going to be a work about the statistical setting, which is quite a bit different than most of what we talked about. So feel free to slow me down and ask questions. And I just want to start by defining the sorts of problems we have. So these are problems where there's some unknown distribution that we want to learn something about. And in the most basic, non-robust setting, we get a sample of IID points drawn from it. We then run some algorithm to learn some useful information depending on the particular task. This includes things like supervised learning, where the distribution implicitly has some function we want to learn. Perhaps we want to learn the distribution itself, and unsupervised learning, where we want to learn the mean or the variance or so on. This really captures most of the ways of formalizing things in statistics and theoretical computer science, where there's a distribution, we get a set from it. Okay, but this workshop's about robustness. Sometimes the real world is not so kind, doesn't give you an IID sample of points drawn directly from the distribution you care about. And so we want algorithms that are robust to deviations from this simple model. I'm going to start with a really classic model of robustness. This one will not be adaptive, so that'll come up shortly. In Hubert concatenation, rather than directly get a sample from the distribution you care about, first an adversary gets to corrupt it. And the way they get to corrupt it is they get to add 10% of some other distribution. And you get IID samples from this corrupted distribution. I like to think of this as a way of formalizing outlier robustness, right? What does it mean to have an algorithm that works in this model? It has to work regardless of the adversary's choices. So no matter how they add 10% of some outlier distribution, you still need your algorithm to succeed and produce a good outcome. But there would be a second way of formalizing outlier robustness that, at least intuitively, is fairly similar, which is an adaptive variant. My animations seem to be doing a full slide at a time, but that's okay. Okay, in the adaptive variant, you first draw a sample of points independently from the clean distribution, and then the adversary gets to look at the sample and choose 10% of points to add. And the difference here between the Oblivious version is the adversary knows the sample before corrupting. So why might this be a little bit more powerful? Well, at least at the level of analyzing algorithms, this can be quite a bit more challenging. Because in the Oblivious variant, you know that there is some distribution getting IID samples from, right? There exists this distribution d hat. You don't know what it is, but in your analysis, you can often work with it. And this is quite helpful. Whereas in the adaptive setting, the adversary can correlate the points, which can affect algorithms. And I'll go over an example later where it actually crucially leads to making the best possible algorithm worse in the adaptive setting. Okay, but a big point of this talk is there are actually many ways to formalize robustness, all with the same general idea of there is a sample of points, but an adversary corrupts it. There are many Oblivious versions where they corrupt the distribution first, and there are many adaptive versions where they corrupt the sample after seeing the distribution. By the way, one way to think of the Oblivious adversary is they still corrupt points, but they commit in advance for what it is they're going to corrupt. They commit to saying, I'm going to add these points regardless of what's in the clean sample, for example. In some other ways you can define adversaries, the subtractive version, which the name kind of suggests what's happening, but you either subtract points from the sample or you remove mass from the distribution. Strong contamination is a particular popular one. This is also called nasty noise in the learning literature. And here they either get to move some fraction of the distribution's mass or change some fraction of points in the sample. And there are many more I could go into here. There are also things that lie between fully Oblivious and fully adaptive. I'm not going to go into details on them, but all of our results will also apply to this intermediate models. We'll be proving an equivalence, and the equivalence will kind of be easier to show for things following unique. Okay, so the main result I'm going to talk about here is proving that you don't need to care about adaptive adversaries. If you want to design algorithms, up to some factors we'll talk about later, you only need to worry about the easier Oblivious adversary. Okay. Okay, so for the remainder of this talk, I want to start with some high-level motivation, a little bit more than kind of definitions of why I think this is an interesting result to prove. Then I want to formalize it because, what does it mean to be equivalent? It's all quite vague right now. And then depending on time, I have a little bit to say about how the proof is structured. I won't go into too many details, but of course, I'm happy to talk offline. Any questions so far? Yeah.
I guess doesn't really matter since you're saying they're the same anyway, but for adaptive adversaries for the other 3 models, are they somewhat similar? Like you do something first, you acquire a sample and then either add a artificial point, like subtract a point, or like just move it arbitrarily?
Exactly, yeah. So just for example here, you will get a clean sample of points run independently from D, and then you'll have some budget, let's say 10%. You get to remove 10% of the points, your algorithm gets 90%. Yeah. Okay, so first some like really maybe almost idealized motivation. I'm not claiming this is what actually happens, but it would be nice if practitioners and theoreticians interact this way. So here's an idealized world where a practitioner, they know they want to say learn the mean, and they know their data is messy, for example. And so they ask their favorite theorist friend, or they look up on the archive for what's the best algorithm for this task, right? Because we have very precise statements about what's best in what context. And so they ask their theorist, and at this point, the theorist is like, I have a bunch of algorithms for you, but I need more detail, right? Is your adversary adaptive or oblivious, and so on? And the point I'm trying to make here is this is much too detailed a question, right? This is like, I don't know, middle school science, I always learned about significant figures. You report as many significant figures as you have an accurate assessment. You don't report like a 10th decimal digit when you only have the first two. That's what I think about is happening here, right? Like in practice, you maybe have some idea your data is messy, but you don't have a formal data generation. And that's really the distinction between the adaptive and oblivious adversaries for the most part, right? It's like a formal specification, but not something that you would expect to have in practice. And it'd be easier to apply if there was kind of a one-to-one mapping between easy to define concepts in practice and definitions, rather than a one-to-many mapping where you now have kind of an arbitrary decision to make about what algorithm says. Okay, and the second pitch is just an efficiency pitch, which is there are many things you want to do with distributions, many attributes you want to learn, and there are many models of robustness. So now you have a big grid, and each grid can be a new algorithm, a new analysis, a new research paper, etc. And so that creates quite a bit of work. You can think about this work as kind of cutting the number of columns in half, and therefore, in some sense, reducing the data, the amount of time we need to spend in half. Okay. All right, and now I want to go into formalizing the result. Okay, so I'll be telling you about the result with Greg. So what we show is you give me any algorithm. It uses n samples to solve some statistical task. I haven't defined what this task T is, so for concreteness, think of it as learning half spaces. But we'll generalize it shortly and we'll apply it more broadly than that. I'm going to give you a new algorithm that will have polynomially larger sample complexity. We'll talk about this a bit more later, but this will be necessary. And what is this polynomially more? Well, it's polynomial of two things. The first is the sample complexity, n, and the second is the log of the domain size. And the way I like to think of this as the number of bits A takes as input is n times log x. And so the number of bits our new algorithm will take as input will also be polynomially large. Okay, and then we will say if this algorithm does what you want when it's corrupted by an oblivious adversary, say learns half spaces, we're going to give you a new algorithm, A prime, that also uses m samples and now does the same thing, learns half spaces in the presence of the adaptive adversary. And the new algorithm is very simple to describe. It takes its larger size m data set and randomly draws endpoints from them. Then it applies the original algorithm on the smaller subset. Now, why is this a reasonable thing to try? Well, the whole power of the adaptive adversary is that it knew what your sample was going to be when it chose its corruptions. And subsampling, in an intuitive sense at least, alleviates this, right? Because you're hiding the information of what it is you're exactly going to use. And I mean, this intuition doesn't tell you how big the subset will have to be. That'll be in the analysis, but at least at a high level, it seems like a reasonable try. Okay, I want to make a few remarks about this. The first remark is that this is a very broad statement. It applies to every statistical task you care about. And it also applies to every variant of adaptive/oblivious adversaries. So I had those 3 columns earlier, and the same subsampling filter will work for all of them. So I like to think of this as like a very general sense in which subsampling, in some formal sense, amplifies robustness, right? It always alleviates the power of adaptivity, regardless of what your downstream task is and regardless of what adversary it is you're working with. The second point I want to make is this is computationally efficient, right? You just run your original algorithm once, and then you need to do subsampling, which is quite efficient. In this particular setting, I would say that's pretty crucial. And the reason for that, I mean, okay, we always care about efficiency. But one additional thing I want to say here is in many robust tasks, there is a naive and efficient solution for robustness in this setting, which is in these formalizations, there's 90% of your data that's clean. You don't know what it is. But often what you can do is just brute force search for the good 90%. you need a way to check you found maybe 90%. That's why it's not entirely black box. But the point I'm making here is, while I don't know how to prove this without computational efficiency, I think it would be less interesting. Okay, and I want to say a little bit about the prior work with Jane, Lee, and Leon, which is that it formalized this question, conjectured it, and then proved it in a special case. Basically, it proved it for certain algorithms with some nice structure, but was not able to give this more general statement. Yeah.
I think you change your sample correctly for the problem.
Yes, it goes from n to m. So it gets polynomially larger as long as your domain size is reasonable.
I see you didn't try to optimize the polynomial, but like what is the
N to the fourth log x squared. And that I would like to say there was no effort to optimize the polynomial, but it started at like 37. But that was more an effort to understand the proof better, rather than not like that proof was very messy. And so naturally polynomial got it better.
Is that an all when x into infinite?
When it's infinite?
Yeah.
Yeah, that's a good question. So okay, two answers. The first is if your algorithm just like only looks at a few bits of each coordinate, you're fine. Like your algorithm, if it's time efficient, is probably implicitly discretizing the domain. And then you can kind of just do that and make the domain size whatever it should be, and the results will apply. If you don't do that, for example, inefficient algorithms, then there's a separation. There's some recent work on distribution testing. I know Gaussian is one of a lot of this. I don't have the other ones, but they show a setting where infinite domains you actually get feasible versus completely domains.
Right, but aren't there like many natural tasks with like adoption data where you crucially use like the rotational invariance in the algorithm, and that you cannot discretize, right?
This is true that rotational invariance doesn't hold up to discretization, but I wonder like if you have an algorithm that's truly efficient, are you like applying rotational invariance, but then when you actually like run the algorithm, you're rounding everything, and I don't actually know if the analysis proved this still works, but if it still works, then it should also work here. That makes sense. Good question. Okay, a few words on lower bounds, which is first for a very natural task. Gaussian mean testing is it's a high dimensional Gaussian. Is it mean zero or is it mean far from zero? There's recent work showing separation. You need at least some polynomial increase in n, so that could not be n times something in log x. And second, for this log x term, in addition to that other work I mentioned, we actually show it's sometimes necessary, sometimes not, and that you can whether it's necessary depends on the type of adversary. So we formalize some notion of the degree of an adversary. What this is whenever the adversary sees one point, how many choices does it have? So in the subtractive adversary, for example, you can either keep it or remove it, constant degree, you don't need a log x. For say strong contamination, every point can be moved to any other point, very high degree, you do need log x. This is mostly characterization with like some gap between upper and lower bound, but roughly speaking, we know what we need is. Okay, I now want to formalize this a little bit more by telling you what class of problems this applies to. This will hopefully formalize intuition. So there'll be like a lot of text on this slide, but hopefully none of it is too complicated. There have been multiple works I found too that formalize in a broad sense what is a statistical task. It's roughly speaking a set of distributions I care about, and for each distribution, what would be a good output. So for example, for learning the mean of a univariate Gaussian in one dimension, I care about all univariate Gaussians, and for each one, I want something within plus or minus epsilon of mean. Okay. That's what a statistical task is. In many settings, like epsilon is a parameter, but this is just all coupled into this one definition. So all of our results will apply for all epsilon simultaneously in any settings where like there's accuracy parameter. Okay. And then what does it mean to solve in the presence of the oblivious adversary? Now we just kind of run through the definition, right? You want one algorithm such that for every distribution I care about, for every corruption of that distribution by the oblivious adversary, with high probability over a sample drawn from this corruption, I produce something in a good set. Okay, and this definition applies to all three examples you saw earlier and other oblivious adversaries. You just kind of change what the legal corruptions are for this adversary when you change which oblivious adversary I'm looking at. Okay, and the adaptive adversary is very similar. Now it's for every adaptive corruption. So the adversary first sees a sample and then decides what to corrupt it to. And you still want this high probability guarantee that for every distribution, for every adversary, you produce something good. Any questions about these definitions?
I'm actually confused about this model of this task because the algorithm's output is only required to belong to this GT and doesn't in any way depend on its.
Correct, yeah, so it will only know S, but its goal is to produce something in GD. So I mean, it won't always succeed. Maybe if it gets a really bad sample, it won't produce something well, but yeah, we measure success not based on the particular sample you get.
Yeah.
Right, yeah,
Sure, makes sense.
Okay, so this includes many things that you can formalize in this one. Okay, and now we can formalize our actual result. And there's some dependence on the failure probability. So you give me something that succeeds with the oblivious adversary with failure probability delta. We make it succeed with the probability 2 delta with a polynomial and whatever delta is.
You probably said this by mistake, so the adversary can like change 0.1% of the data, let's say, or something like that.
So is your question like how much of the data?
Yeah, how much the constant fraction? Yeah.
Yes, that is the most common setting where you define it as a constant fraction. Our results apply regardless. So there are more than the three, each column adversary is implicitly like many possible definitions parameterized by what fraction. So as long as we use the same fraction for both the oblivious and adaptive, our results apply, and that can be any fraction.
But if like the corruption is 100%, you can really solve the problem.
Yeah, if it's 100%, then you can't do anything. Yeah.
Oh, but like if it's like 1 minus 1 over n, still exceptional.
Oh, sorry. I think actually I should add, it should be a constant because the sample sizes are different.
Right.
So in order to make them the same, you need the same constant fraction is corrupted. So if it's like 1 minus 1 over m in one of them and 1 minus 1 over m in the other, then I'm not sure what you would get. If you only have one clean point, I think for most interesting tasks, you shouldn't be able to do anything.
Yeah.
But you can like define like here's an artificial task, output something with non-zero probability in the support.
Yes.
Even one clean oh no, you don't know which is clean. I take it back. Okay, even that task, but I'm sure you can come up with.
But it doesn't include tests where you have like more than percentage, you feel like this coding is.
Yeah, then you're like, what it needs to be a good output would be a list of things, one of which is good, and this would stand test. Yeah, as long as you can write it as a statistical task with some output set, you're good. Yes, for this statement, but in many settings, you can do amplification to get an exponential dependence. So you get like, you go from any constant here to a constant here, and then apply black box amplification for your specific task. So yeah, if you want this subsampling statement, you need it, but many times you can get around. Okay, good. So now I just want to say a little bit about the structure of the proof. This is the part where I could stop at literally any time, it would be fine. So we'll just see wherever we get. I'm just going to kind of say the structure of the proof. There won't be like proof itself, but formalize like how is it that we prove such an equivalence. And we prove a simulation lemma, but there are like a lot of caveats to formalizing these statements. So all of them will be necessary. Well, the next slide will kind of give details on what it is. But we show for any adaptive adversary, there exists an equivalent oblivious adversary, but this adversary must be randomized, whatever that means, and there must have been subsampling some culture. And so on the next slide, I'll formalize this. Okay, so give me any starting base distribution and any strategy for the adaptive adversary. And this is going to formalize an entire data generation procedure that I'm going to want to. So the strategy is it's a whole function from every clean sample to every corrupted sample. And now the whole data generation procedure is first draw a clean sample ID, corrupt it from the strategy, and then subsample it down. This sample T is what the algorithm A is going to eventually get. And now I want to say that there exists an oblivious adversary. It's actually going to be a distribution over possible oblivious adversaries that mimics this. So the data generation procedure on the right is going to be draw a random oblivious adversary, so a random corruption. Then draw an IID sample of points from this corruption. And our guarantee is there's always a way to do this, such that for any parameter delta, as long as you choose M appropriately, the distributions over samples you get is close to TV distance. So this random variable T and this random variable S will look quite similar in TV distance. Once you have this, our main result applies pretty easily, right? In order to prove A prime, the like subsampled version succeeds on any adaptive adversary, well, we knew that A succeeds with every oblivious adversary, and you can pretty easily show it succeeds on any randomized oblivious adversary. And since these are indistinguishable, you get the result you want. Actually, more interestingly, and I didn't realize this at first, you can actually show that this statement is equivalent to our theorem. The other direction is an application of the mini-max lemma, and that that motivated us to simplify our proof and realize this and take something that was not of this form, turn it into this form. What time? You know what time I started?
5 more minutes.
Good. Then I will just say I have a couple last slides that say, like, where does this randomized strategy come from? Like, why is it randomized? And I'm gonna just like give you the construction of the Oblivious adversary given the adaptive adversary without any proof of why this construction works. Okay, so the construction has 2 phases. The first phase is group together similar adaptive corruptions. So remember, the adaptive adversary is a strategy mapping clean samples to corrupted samples, and it can make different choices on different samples. You intuitively want to group together similar ones. So this might be one corruption, we'll put it on the left group. Maybe on this sample, it makes a different corruption. This looks quite different, right? Like the cluster of points created is in the bottom left, right in the top right. It's removing like different sections. So we're going to say totally different, put it on the right. And we can repeat this with every possible corruption the adversary can make. In this slide, I'm depicting 2 groups. We'll actually have like some fairly large exponential number of groups. But the point is we group together similar corruptions. And the Oblivious adversary is kind of only going to try to succeed on each group. Now, the question is, how do you kind of automatically group together things? Like it's a proof. I'm not sitting there like, forwarding everything myself for each adaptive adversary. The proof needs to specify what the groups are. And it's pretty simple. We group together, I guess the colors don't show up very well here. We group together points, we group together samples that share a lot of points, what we call a core. So I'm not sure how well the color shows up, but all of these 3 share the same set of roughly 15 points. And similarly, all the other 3 share the same set of roughly 15 points. And the intuition is that if you overlap a lot, you should be somewhat similar. And kind of the adversary can't force lots of samples that overlap a lot to be different on average. Everything's very average case here. Okay. And then once we have these groups defined, we then just round each group to its nearest Oblivious corruption. So we try to find an Oblivious corruption, such as if you take IID samples from that corruption, it mimics subsampled versions of things. And there's some analysis that shows if you do this, you choose the group size correctly, you're actually going to have small error on average over the groups.
Do you need the finiteness of X to do the grouping itself? Or argue about this rounding?
Good. So you would have infinite groups, and your distribution over Oblivious adversaries would be infinite size support. But we can still show that the final result won't depend on log X, for example, for subtractive adversaries. So like you can define everything, whether it has a dependence on log X requires more information. But yeah, it's easier to think about when everything is discrete, in which case like even the amount of groups is fine.
Yeah.
Okay. Yeah, then you just do the distribution over these. You give weight to the different Oblivious adversaries in kind of a natural way. Like if the adversary half the time does this, half the time does that, it's 50-50. If they do one type of corruption more often, you also give more weight to the corresponding part of the Oblivious adversary. Okay, and using this strategy, we're able to get that this will mimic the adaptive adversary up to some small TV distance bound, which implies our main. Okay. Just to close, the reminder is we've proved adaptive and Oblivious adversaries are equivalent up to polynomial factors, which we do know are necessary. We don't know the exact polynomial factor, but we know something is necessary. And I want to close with a more broad question, which is this is proving a notion of equivalence for what I would say are intuitively somewhat similar adversaries. They differ in this one attribute. But I think it'd be interesting to explore more broadly how robust robustness is in this setting. Like, can you prove equivalences, say, between these 3 columns? And here there's already been some work in this direction. It seems to require some structure. It's not going to be quite as black box as this. But empirically, it appears to be that, often when we come up with one robust algorithm for a task, we can come up with other robust algorithms. It'd be nice to formalize this, empirical intuition. Thanks. Any questions?
Yeah, so do you have any assumptions on the distribution? Like, are there distributions that are easier to attack?
There's no assumption in this result. For your second question, the distribution is easier to attack. I'm not sure. Yeah, I mean, maybe if distribution is like has very low entropy or something, then you can say attacks are easier. But yeah, I don't know. This has no assumption on distribution.
Yeah. You mentioned splitting the types of adversarial strategies into like different cores.
Yeah.
Is each strategy characterized by like multiple possible cores?
Good, yes, this is a good question. So, here's each of these samples, these groups are not disjoint, that is your question. Yes, because what group you're in is a function of what cores you have, and you have many possible cores. So I simplified it here by saying like, just tell me which type of structure this is, but in actual strategy, the types overlap. Is that your question?
Yeah, so I guess, I mean, don't you like go over something like 2 to the x kind of options, which is too much, you know? Is it,
It's like X.
how come it's efficient?
Yeah, good. So the size of the core will be some primitive k, and the number of possible cores is like, oh, sorry, efficient. Good. This is for the adversary. The adversary is allowed to be inefficient. Sorry. Yeah, so we just showed the existence of an oblivious adversary. We're trying to defeat even inefficient adversaries. If that makes sense. So this, none of this has to be constructive, except I don't know how to prove it, except if it's like somewhat constructive, if that makes sense.
The adversary is these separations that we talked about earlier, these still.
Yeah, so I don't remember what would happen for Gaussian identity testing. There's a very simple separation you can do for support size estimation. So you have a distribution over a known domain, you want to estimate how many samples are in the support. With subtractive adversary, the adaptive version can remove all collisions. The oblivious adversary can't remove any collisions, and that's very efficient. So if you remove all collisions, you essentially get no information. So yes, I need to think about other, but this one at least.
Any other questions? Okay, thank you.